Welcome to this explainer. Today, we're diving into the seemingly magical physics of pressure. We're going to break down some seriously powerful concepts that literally surround us every single day, so you can master exactly how these invisible forces actually work.
So, let's start with a riddle. Have you ever wondered how a mechanic can effortlessly lift a massive 2-ton car with just the push of a tiny button? Or how a colossal iron ship weighing thousands of tons can float gracefully on the ocean, while a tiny little iron ball drops straight to the bottom? Honestly, it almost feels like a physics cheat code, doesn't it? Well, stick with me, because by the end of this explainer, you're going to completely understand the brilliant science that makes these everyday engineering marvels possible.
All right, let's kick things off with Section 1, the power of pressure. Before we even touch pressure, we really have to talk about thrust. Thrust is simply a force acting completely perpendicular or, straight on to the surface of an object. Think of it like a direct head-on push. And just like any force in physics, its standard unit of measurement is the Newton. Now, what happens when you take that thrust and spread it out? Boom. That is where pressure comes in. The golden rule here is this. Pressure is just the thrust, or force, acting perpendicularly per unit of area. The formula? Super simple. It's force divided by area. So when 1 Newton of force is applied over exactly 1 square meter, we get 1 Pascal of pressure. Which brings us perfectly to Section 2, Pascal's force multipliers. Imagine you take a plastic bag, fill it with water, poke a bunch of holes in it with a needle, and just squeeze. What happens? Well, the water shoots out of all those holes with the exact same pressure. This perfectly proves Pascal's law, a concept discovered way back in 1653 by Blaise Pascal. The law basically states that when you apply pressure to a liquid in a closed container, that pressure is transmitted equally and perpendicularly in all directions. Because liquids are pretty much incompressible, that pressure literally has nowhere to hide. So, how do we use that equal transmission to our advantage? Take a look at this U-shaped tube. It's what we call a hydraulic machine. We've got a small cylinder, let's call it area 1, and a much larger cylinder, area 2. When you apply a small force on the small piston, it creates pressure. And according to Pascal's law, that exact same pressure travels all the way through the fluid to the large piston. But here's the kicker. Because area 2 is so much larger, the resulting outward force has to be much, much greater just to keep the pressure equal. It essentially makes this machine a literal force multiplier. And this isn't just some chalkboard theory, right? This is literally how heavy industry operates. The exact working principle we just broke down is exactly how hydraulic car lifts work. You apply a relatively tiny amount of force to the small piston on one side, and the liquid just amplifies that force across the massive surface area of the big piston, effortlessly hoisting a heavy car right up into the air. Actually, we trust our lives to this principle every time we hit the road. Check out this hydraulic brake system, the kind used to stop massive vehicles like trucks and buses. When you press down on that small foot pedal, brake oil gets pushed out of the master cylinder under pressure. It shoots through the pipe into the wheel cylinder where, you guessed it, the pressure is multiplied. This forces the brake pistons outward, slamming the brake shoes tight against the rotating wheel drum and bringing a speeding truck to a completely safe stop. All right, shifting gears a bit. Section 3, the science of upthrust. When you drop something into a liquid, the liquid actually pushes right back. That upward push, that's called upthrust. It's the resultant force exerted by a liquid in an upward direction. This is exactly why a heavy rock suddenly feels like it's lost half its weight when you try to pick it up from the bottom of a pool. Let's scale this concept up in Section 4, Archimedes and floating ships. Okay, back to our riddle from the very beginning. Since both of these things are made of the exact same heavy iron, why in the world does a solid iron ball sink straight to the bottom, while a colossal ship built from that same heavy metal manages to just float beautifully on the surface? The secret here lies in Archimedes' principle. This principle tells us that when a body is partially or fully submerged in a liquid, it experiences an upthrust that is exactly equal to the weight of the liquid it pushes out of the way. Look at these Eureka can experiments. When the object gets lowered in, it pushes water out and into that smaller beaker. If you were to weigh that displaced water, its weight perfectly matches the amount of upward force, the upthrust, acting on the object itself. And there is the answer to our riddle. A solid iron ball is just too compact. It simply can't displace a volume of water that matches its own immense weight. So the upthrust isn't strong enough, and down it goes.
But an iron ship? It's cleverly shaped. It's hollowed out. Its massive volume allows it to push aside an absolute ton of water, literally, enough water to equal its own weight. This generates massive upthrust, fully supporting the ship and keeping it afloat. Now, I want to point out a quick but super important distinction between Archimedes' principle and the law of flotation. Archimedes' principle applies to absolutely anything you put in a liquid, whether it sinks like a stone or floats like a cork. It just calculates the upthrust. The law of flotation, however, is a bit more strict. It applies only to floating bodies, stating that for a body to float, its weight must be exactly equal to the weight of the liquid it displaces. So here's the real trick. If you can manipulate your own weight relative to the water you displace, you can actually control whether you sink or float on demand. And that is exactly what a submarine does. They use these things called blast tanks. When it's time to dive deep, they flood those tanks with seawater, instantly increasing the sub's weight so it overpowers the upthrust. To shoot back up to the surface, they just blast all that water right back out using highly compressed air. The weight drops dramatically, the upthrust takes over, and up they go.
Let's take this whole concept sky high in Section 5, floating in the air.
You see, just like a pool of water, the invisible atmosphere all around us also exerts upthrust. A hot air balloon pilot is essentially sailing on this atmospheric upthrust by playing with air density. First, they fire up the burner to heat the air inside the balloon. Hot air is less dense than the cool air outside, meaning the balloon is displacing a massive amount of heavier, cooler air. This creates an upward push that's greater than the balloon's weight, sending it into the sky. When the pilot wants to just hang out and hover, they balance the temperature so the upthrust perfectly matches their weight. And to land, they just kill the burner. The air inside cools down, gets denser and heavier, the weight finally beats the upthrust, and they drift safely back down to Earth.
From force-multiplying liquids bringing 2-ton cars to a screeching halt, to the massive upthrust keeping iron ships and hot air balloons afloat, seeing how basic pressure unlocks this kind of immense power really makes you look at the world a little differently, doesn't it? So the next time you hop in a car or step onto a boat, ask yourself, what invisible forces are secretly holding you up right now? Keep questioning, keep learning, and hey, thanks for joining me on this explainer.